how wonderful that you came on the last day. Right? These are the hardcore with plenty of practice. Anyhow, it gives me great pleasure to introduce Richard Nickl, who's going to present the fourth and final keynote lecture of ISBA 2022 World Meeting. His talk will be Bayesian nonlinear inverse problems in high dimensions. Let me tell you a little bit about Richard. Richard grew up in Vienna, right, where he received his PhD from the University of Vienna in 2005. On a personal note, I had the great good fortune to first get to know Richard at a conference on model selection in the summer of 2008, right on the ground floor. An immensely clever good guy, lots of fun. Right? He was about to join the University of Cambridge as a lecturer that fall. What a joy for me to watch his meteoric rise from those early days. Having established himself quickly as one of the leading mathematical statisticians of his generation worldwide, right, with remarkable contributions to non-parametric and high-dimensional statistics, empirical process theory, and Bayesian inference, hooray, for statistical inverse problems and partial differential equations, Richard is now professor of mathematical statistics at Cambridge. A few things: jointly with the late Everest Genet, Richard co-authored the book Mathematical Foundations of Infinite Dimensional Statistical Models, which won the 2017 Prose Award of the American Association of American Publishers, right, for Best Monograph in the Mathematics category. He is an invited speaker at the 2022 International Congress of Mathematicians. He was an invited speaker at the 8th European Congress of Mathematicians. He was awarded the 2017 Ethel Newbold Prize of the Bernoulli Society, and in 2015 was a recipient of a Consolidator Grant Award by the European Research Council. Right, it's one of those giant ERC awards. Richard, take it away.
Okay, thanks, Ed. These are way too nice words to introduce me. It's great to be here and to give this talk to a Bayesian community. So I'm not a hardcore Bayesian by birth. I worked more on mathematical statistics generally, but mostly through the influence of Ad and others. I did start to study Bayesian problems probably about 10 years ago. And in fact, the last few years, I've been studying some problems that pop up in data science in an area maybe slightly remote from what is happening here, which is sort of in applied mathematics, physics, scientific applications where people use partial differential equations to model physical phenomena. And actually, if you go to these communities, many of them, if not all of them, also use Bayesian methods in high-dimensional sort of statistical problems. They are not sort of academic statisticians, maybe, as many of us here are. But the problems are very interesting, partly because they use Bayesian methods, so it's interesting to understand their performance and see why they use it and what the advantages are. And also partly because these models are just interesting statistical models and problems. And I'll try to convey some of the recent developments in this area. I'll focus the first half of the talk to just sort of basically explain roughly what's going on in this area. And then my own contributions are more towards a theoretical understanding of the performance of these algorithms in high-dimensional situations. And so I'll spend the second half of the talk maybe describing a bit of the progress we've made in the last few years on the understanding of Bayesian algorithms. And then also I'll point out some of the many open problems. I've been working on this for a few years now, and I've had many people in my group in Cambridge that then went to other places, and also collaborators. I can't mention all of them now. Those that are specifically relevant for this talk are Jan Bohr, who was a PhD student in Cambridge, who is moving to Bonn now, and Sven Wang, who's also a PhD student, who is now at MIT. And then my collaborators or colleagues, Gabriel Paternain and François Monard. I also gave, if you're interested in these kind of topics, they're a bit inaccessible if you just read the papers that we've written, because they often get a bit technical when you do PDs. But this spring I was giving a sort of advanced graduate course at the ETH Zurich, and I've written up some lecture notes on this, which eventually will be published, but I've put the sort of first version on my website now, so you can check this out. This is a more pedagogical document than the papers that we've written. So you can find that on my website. Okay, so roughly the best way to explain what these statistical models are, and I'll give some examples later, but actually these are just regression models. Okay, so they're sort of standard response variables, yi, yeah, the cursor is here, and you have your covariates xi. Just that these regression functions are sort of very particular functions, and I'll try to explain what they are and how they arise in a moment. But other than that, it's just standard regression. No? So you have, and these regression maps are typically defined on some d-dimensional domain, could be the cube or something else. So let's, and of course you discretize this domain into some points xi's, where you take your measurements of this regression map, and you get responses corrupted by additive error, which we might as well assume to be Gaussian. That's not crucial for the theory, but it's certainly handy to explain the ideas. Yeah? And so just notation, this response and covariate vector of all the data we've observed, we'll call that d sub n. And sample size is n. Okay, so we just have n typical regression measurements. So far, that should be okay for anyone. And so these regression maps are, there's sort of a nonlinear story going on. I'll explain that, we'll get to that repeatedly, but basically there's one set of functions which are the thetas, which are just functions you're trying to infer from your data, but you do not observe these thetas, you observe some other functions, g sub theta. Yeah? So you basically have a regression function parametrized itself by an infinite dimensional parameter. You could think of just the usual non-parametric regularity classes that we use in statistical theory, like you say that the theta functions are functions that have alpha derivatives, so H alpha spaces. And typically in these applications, your data might actually not be scalar, but you will have some vector valued observations. We'll see examples in a moment. So we could say that these regression fields take values in some vector space V. Okay, but for the talk, I'll just stick to V equal to R. Just to keep the notation simple. Yeah, and so what are these G thetas? Well, the first sort of really what they do is they describe a physical phenomenon that is modeled by a partial differential equation. Yeah, so there you see these maybe sometimes in science talks, like in maybe weather forecasting or something else. They write like down a huge system of equations, differential equations that describe somehow the dynamics of what you think you're seeing, and then you take measurements of that, and you have some parameters in this system of equations, which would be the thetas, but you don't measure that. You just observe the weather, which is sort of the solution of this system of equations. And so formally, the theta would be again the parameter, and what you actually observe is a solution of a partial differential equation in multi-dimensions where the solution depends on the theta that you don't know. Okay, but it's just regression. Okay, it's just a nonlinear regression model. So what kind of examples can one have in mind? Maybe very classical examples from inverse problems is non-invasive tomography. No? So you have some medium that you want to image inside, but you don't want to slice it up. So you shoot some rays through it, or maybe do some other physical measurements, maybe send a magnetic field through it, something like that. And actually, many people sort of view this just as standard like integral geometry, but they actually are closely related to a class of first-order partial differential equations. So in some sense, if you study transport PDEs, you will always have applications to these sort of tomography methods. I will not talk a lot about like details of PDEs. You just have to believe me on this one here. Maybe the most important general class of such differential equation models pop up in sort of data assimilation applications, time evolution equations, like in geosciences and weather forecasting, where you sort of have a phenomenon that evolves with time. But again, maybe think of Navier-Stokes equations or wave equations. You want to sort of infer parameters from taking discrete measurements of the physical system. And for the theory, often initially, or also for your first understanding, it is helpful to just deal with maybe the most commonly or the best understood class of PDEs, which are elliptic second-order equations, which also pop up in applications, but they're particularly useful to develop sort of first theoretical results about algorithmic performance. Yeah? So now, if you want to get a more exhaustive list of applications, I send you to two papers in sort of the top numerical analysis journal or scientific computing journal, which is Acta Numerica. So there's a famous paper that I will mention later also by Andrew Stewart, who popularized Bayesian methods in such PD models. And there's a more recent survey by Simon Arridge and co-authors also in Acta Numerica. And actually, just to maybe illustrate the importance of these methods in applied mathematics, there's a whole SIAM journal of uncertainty quantification, which sort of basically deals with problem of this type, and where most of the papers are about how to use Bayesian methods to quantify uncertainty in algorithmic outputs. Yeah, so we'll see how Bayes works in these settings, but the key advantage of Bayes of other methods is that you automatically can quantify uncertainties by credible sets and posteriors, which is really crucial in these applications, because one typically has like several parameters that one wants to infer, makes certain measurements for one parameter, and then you get some reconstruction there, and you feed this into the construction of your new measurements. So if you don't have error bars for your initial recovery, you can't really proceed as an engineer or as a physicist. Yeah? So it's very important for them to have guarantees for their algorithms. Okay, I will not talk much about any concrete applications today, but they abound, these applications. Yeah? And in some sense, they're actually older than the current hype of data science. Yeah? So these are like sort of maybe the old sort of good inference problems that scientists and physicists would have studied already for decades, if not maybe a century or so, where you want to understand sort of a coefficient that describes some physical dynamics. But of course, with the advent of data, of huge high-dimensional data sets, also these disciplines are being transformed. They kind of want to use algorithms that can extract sort of more information from in high dimensions, and so somehow there's a nice confluence of sort of traditional PD models and modern algorithms for data science, and Bayes methods have established themselves, with great empirical success in this literature, but with not so much theoretical guarantee so far. Yeah. So there's maybe I could say fruit fly example that like people test their methods on, both for applications, numerics, and theory, that sort of you can use to illustrate what a typical such partial differential equation would be. So you have a diffusive phenomena, and maybe we just make what we call a steady state measurement. So you can make these measurements from a heat equation dynamics. So what you have is you have a diffusivity or a conductivity inside of your medium that sort of describes to you how easy it is for heat to flow through, or for how easy it is for sort of electricity to be conducted. And this will be modeled by this f theta here, so that has to be something positive. And theta is a function that is sort of the unknown parameter. So you want to maybe up to the logarithm here, you want to understand sort of how heat will travel through your room or your space. Okay, but you do not measure, of course, the diffusivity or the conductivity itself. What you measure is just the heat distribution in steady state. So that would be the solution of this PD here. Yeah, so you take you postulate that the solution exists. One can show that they exist. Of which you take the gradient, this is a vector, and you multiply it by this conductivity or diffusivity f theta, and then you take the divergence of these vectors, you just sum up all the partial derivatives, and you declare that this equals some source g, and you have some boundary temperatures h at the boundary of your domain. Yeah? And so equations of that kind, in dimensions 2 or higher, you can't solve them explicitly like in ordinary differential equations, like in classical mechanics, so you don't know what the solution is, but it exists and it is unique by theorems from functional analysis, okay? So you can then ask yourself, well, if I measure only the solution of this PDE, that's my regression function, can I somehow sort of, go back and solve for the inverse of this and find the f theta in this equation? You can, of course, there are lots of differential equations. Other second-order examples are where you have a fixed differential operator that describes some dynamics that you know, and you perturb it by some potential, this f theta here, and you want to see how sort of the solution changes when you sort of subtract this term. When d is sort of the standard Laplace operator, this is what you call a Schrödinger equation in steady state. But already when you take a first-order differential operator for d, this is a set of equations that describe X-ray problems. Yeah? So you will not see this immediately, but you can study the solutions of this equation, and actually along each sort of geodesic through your domain, the solution of this will precisely be the Radon transform. Yeah? So there's this PDE connection. But this, of course, works for general operators. And studying these problems from a PDE perspective is actually often more insightful than writing down integral transforms. Okay, and so this is how your regression functions arise. They are kind of given as solutions of these equations that depend on unknown coefficients indexing your differential operator. And in these model examples and in most of the other interesting ones, the key challenge for the statistician is that the map that sends your theta parameter to the solution of the PDE is not linear. Yeah? So these are not linear regression models. They are non-linear regression models. And the nonlinearity is not one that we can write down. The nonlinearity is forced upon us by a partial differential equation. So there is structure, but it is not obvious structure that we can sort of represent easily. Okay, and sometimes you don't even measure, in non-invasive situations, you don't measure the solution of this PD just like everywhere, but you might only measure it at the boundary, maybe what you call scattering data, which of course makes life harder, but then you might choose to take several measurements at the boundary by just varying maybe the boundary temperatures or something like this, so you can accrue more information in these experiments. Yeah? So there's sort of a general setting, and this G map will be sort of my mathematization of this regression function that pops up in these applications. So just as an example, the basic example, if you look at the Laplace equation, when you have a constant conductivity and your domain is this annulus on the right-hand side, and then you can prescribe some boundary functions. So then the solution of this elliptic PD, so the regression function you see, is actually the object on the left. Yeah? So it's a harmonic function, and this is sort of the base example that would correspond to a constant, sort of the easiest constant conductivity. And then as you vary the conductivity, of course, the solution of this PD will also look different. Yeah? And so you want to somehow go back from more complicated pictures like that to the original conductivity. Just to illustrate this in an X-ray problem, a non-abelian, like a matrix X-ray problem, here again, the theta parameter would be a magnetic field, so you actually have a vector field of 3 functions that you want to make inference on, so 3 non-parametric objects, which are just here, these superpositions of sort of little Gaussian bumps on the disk. And what you measure is sort of X-ray transforms in a Lie group here, so you basically get these real and imaginary parts, which correspond to the left and the right column in the bottom display. Yeah? So what you want to infer is like basically the top sort of 3 functions from data like down here. And it's clear if you just look at these pictures that there's no obvious way to go back. Yeah? So you need to understand the mathematical structure of this forward map G. So this G, in inverse problems, this G map is what they call forward map, because it sends the theta parameter that you want to make inference on into the forward data, which is the solution of your PD. Okay, so these are kind of problems that for us as statisticians, we can just say, well, these are regression models, non-linear, and we have a bunch of conditions on them. Yeah? So, and what are the discerning features on these G theta maps that make it difficult? So I could give you now like 10 PD examples and tell you, well, this is hard, blah, blah, blah. But like having worked on this now, let me give you a list of reasons or of things that I encountered in my work that make this sort of non-standard compared to maybe commonly used statistical regression problems. So the first is, well, yes, this solution of the PD exists, but I cannot write it down analytically. Yeah? So in one dimensions, we can solve differential equations by just the fundamental theorem of calculus, but in multi-dimensions, what you say is, well, there's some injectivity estimate, so yes, there is a unique solution, which comes from some inverse, but that doesn't mean you have a formula for it. Yeah? So we know that there is some abstract solution, but we don't know what it is. Yeah? So you can't like write down a formula. What we can do, we can, like what people in scientific computing and numerical PDs will tell you, we can solve these PDs numerically. So if you give me theta, and I discretize my theta in some sort of, a grid on my domain, then I can give you a numerical solution of this partial differential equation. So I can kind of, when I plotted these pictures just before, of course, that's just what I did. Yeah? Okay, so there's a well-established numerical toolbox in applied mathematics, finite elements and these things that will tell you how you can actually compute the forward maps. You can evaluate, so later this will be related to the likelihood function that pops up in the Bayesian formalism, so it's important that we can evaluate this thing. Yeah? If you can't evaluate it, it would be too hard. Another aspect in many of these examples is, and that's where the inverse problem comes in, that these G maps are smoothing. Yeah? So if you take a theta that has a prescribed regularity, then actually the G of theta will be a bit smoother. Yeah? And so in information theory, of course, if you think of it for a statistician, if you have a complex object that when you measure it looks much smoothed out, you lose information. Yeah? So going back will be hard. In some sense, the inverse map should be ill-conditioned and not continuous. But even before you talk about the inverse map, you have to prove that this is an identifiable statistical model, which is also not clear for many of these examples. So it's not clear that the coefficient of your PD can be recovered from the solution of the PD. So proving injectivity for these maps is often, this is a sort of well-established area in pure mathematics, where sometimes proving something like this for a big problem for a set of PDs can end up being a few papers in the Annals of Mathematics. Yeah? So these are not cheap problems. Yeah? But often you do get this injectivity, so there is a well-posed statistical problem where you could say, well, actually, at least in principle, I should be able to find theta from G of theta, but, as I've said before, this inverse map is not continuous in the distances that statisticians like. Yeah? So we think we can recover the regression function in some L2 sense, but if I want to go from g of theta back, I need to be able to make inference on the regression function in a much finer sense. I need to know more about it than just sort of L2 inference. So the inverse map is not continuous in the relevant topology, if you want. Yeah? So I can't just like do non-parametric smoothing on the regression map and like try to go back. Yeah? So that's not a recipe. In particular, there's no inversion formula. Yeah? So classically linear inverse problems, like the Radon transform, or even if you want even Fourier series, they give you a nice reconstruction formula. Yeah? So they tell you you can write theta as some integral of g of theta or something. Yeah? And that's beautiful, and you can try to numerically discretize it and make it robust to noise when you have such a formula. But in these nonlinear problems, you don't have it. You just know that the inverse exists, but no one knows how to write down numerical formulas for G inverse. And also, the set of, if you want, PDE-constrained regression functions. So if you think of the space of all regression maps, then the regression maps that you're going to see in these models is a sort of very special subset, because there are only functions that are solutions to these PDEs for some theta, and this is sort of a non-linearly constrained subset, so you can't just describe a projection onto it. Yeah? So you could do some naive sort of regression estimate and then project it, but this is not something that you can do numerically or even in principle. Yeah? Okay, so these are sort of ways where maybe sort of the standard toolbox, at least from non-parametric smoothing, does not work, but Bayes should be able to deal with this in a beautiful way, as has sort of been realized in this literature, maybe independently of our more statistical community. So how does that work? So Andrew Stewart wrote this paper in 2010, basically proposing to solve problems of this kind in a Bayesian way. Maybe he hasn't done much more than writing down Bayes' formula and suggesting good MCMC algorithms for the use of it, but seeing that this works, and for reasons I will spell out in a moment, was still an important contribution. Okay, so if we stay in this random design regression model that we had from the first slide, well, we know what the log likelihood function is. No, it's just the negative least squares fit, where I sort of look at how well I can explain my responses by the candidate solution of my PDE evaluated at the measured xi's. Now, because G is nonlinear, this is not convex. Yeah? So it's not, so negative of ln is not convex. Okay, so if you wanted to do optimization here, you have to, in principle, expect that there will be multiple modes, and you can't just run a naive optimization method. Yeah? So in that sense, it connects nicely to challenges of modern data science, that these are all non-convex problems. Yeah? So we can't go back to the toolbox of high-dimensional statistics and just do that. But of course, the nonlinearity is described by PD, so it's not completely arbitrary. So we want to exploit this structure in sort of understanding the local surface, the local properties of the posterior surface. Well, what is the posterior? Well, because the G inverse map is kind of discontinuous, independently of being Bayesian, it makes a lot of sense to penalize too rough thetas, yeah, too rough sort of solutions of your problem, because you expect that when you go back, you need to regularize. And the Bayesian approach does this more or less automatically by the prior. Yeah? And I think really, for these people, the prior is a tool to regularize and not something subjective at all. And of course, the most attractive priors that are used for implementation, although other things are being used, but at least initially, would be Gaussian process models for the theta. Yeah? So theta is a nice function that you're trying to understand. Typically, you can make it live in a linear space by maybe taking a log transform or something like that if it's positive. So you choose a Gaussian process model for your log conductivity, for instance. And so the posterior distribution, of course, I don't have to explain this here, will just be the reweighted log likelihood, which if you think about it without wanting to be too rigorous now, your Gaussian process prior has a reproducing kernel Hilbert space norm, which describes how much you regularize or penalize. And so in the posterior formula, you'll just get e to the log likelihood and then minus the penalty squared. Okay, so and if you choose, for instance, an H alpha regular Gaussian process model, you will basically just take the log likelihood and subtract this quadratic Sobolev norm penalty. Now, if you do maximum a posteriori estimate, you do the same as what people call penalized least squares, and this is not maybe so interesting, or sometimes called Tikhonov regularizer. But of course, for the Bayesians, we have the MCMC toolbox. And this is here now in these nonlinear problems where really optimization theory and Bayes departs, not just philosophically, but also really algorithmically. Because if I compute the posterior mean instead of the mode, I'm doing something very different. Yeah? So they do not coincide any longer in this nonlinear setting. So I'm actually solving a class of PD problems, not by maybe more traditional optimization methods, but I'm doing Bayes. I'm going to run MCMC to compute this. So I cannot even analyze this by optimization methods. You really have to understand Bayesian statistics if you want to understand what this does. And people do it because these iterative schemes for MCMC that one can use to sample from these posteriors often scale reasonably well in the problems they have. Okay, so but it is for the statistician. It's very interesting that, of course, here you really, in some sense, come into a territory that cannot be analyzed by variational optimization tools. Okay. Okay, so there are, of course, many MCMC methods that you can try to use. I will not present all of them here. I will present the one for which I can give some theorems about computational guarantees in these non-log concave or non-convex settings. So this is, based, sometimes called unadjusted discretized Langevin algorithm. What is it? No? So when you implement, okay, we still have an infinite dimensional model, but of course when you run this with real data, you will take an approximation space in high dimensions that you could take from some maybe basis functions that could be either some wavelet splines or whatever. It doesn't really matter so much. It has to be an appropriate space that pops up in the theory. But what you do, you will just do some sort of gradient based Monte Carlo scheme. Yeah? So you initialize at some point, then you compute the gradient of the log posterior, which you can do as long as you can evaluate G and the gradient of G. So you just need to solve the forward PD. You don't have to compute G inverse to make this step. Yeah? So that's the crucial observation here. So you don't have to find an inversion formula. And you take these little gradient steps, delta is your step size, and you add some Gaussian innovations, which is sort of the discretization of the continuous time diffusion process that is called the Langevin diffusion, which sort of up to the discretization error will be a Markov chain that precisely targets the posterior distribution. Yeah? So it has invariant measure very close to the posterior distribution. And now you just run your gradient method. Maybe after some burn-in time, you keep collecting your samples and you take the average of this gradient scheme. Of course, you could do any other MCMC scheme, but let's stick to this one. And then you can ask yourself, if I use these ergodic averages here, can I give any guarantees if I use that this recovers and solves my inverse problem? Okay? But before I ask about guarantees, you can just do it anyway, and people do it and see that it works very well empirically in a large class of applications. And just to make the point, why has this been so successful in inverse problems? If you want to do these gradient steps, you need to compute the gradient of the log posterior. The log posterior, of course, is just the gradient of the log likelihood plus the gradient of the prior. The prior is Gaussian, that's easy. And on the log likelihood, you need to evaluate G and the gradient of G. And this is something that the people know very well from numerical PDs in their problems, because the forward thing is what they know how to do, like from decades ago, more or less. Yeah? So they have very good tools to compute the G map and also its gradient. What they do not know is how to compute G inverse. But this method, this algorithm, doesn't require you ever to compute G inverse. And that is why it is so successful, because you can just run it without thinking about an inversion formula. In particular, it puts all these people who try to prove inversion formulas kind of out of business, yeah? Because you can use an algorithm that never speaks about an inversion formula. Yeah? And so it is somehow, when you go to this point, the fact that Andrew Stewart suggested this at this time, the reason why it's successful is because it solves a large class of problems without you even speaking of the inverse step. Now, if you're a scientist, of course, if you're maybe just a scholar, maybe, you should also say, well, wait a second, but it has to be too good to be true, because I've written this down, and I've never even checked that G is injective. So this could obviously be complete nonsense. I can use this also in a non-identified model. And so if I'm not careful and give some algorithmic guarantees for it, I might just reporting random numbers. Yeah? So I think it's a very important point here for theoreticians to start to say, well, okay, let's check and see whether there's any hope that methods like this can work, because otherwise it opens the door to abuse of these algorithms in cases where your model is not even identified. Okay? But you can see the methodological appeal of the method. Okay? Okay, and we've implemented this in this non-abelian X-ray model. So, and you see actually it works really nicely. So here you have sample sizes of 200, 400, 800 in each of the rows. We ran it for quite a long time, 100,000 MCMC iterations. So it's not super fast. It takes a few hours for sure, but still. You get reasonably nice pictures already for moderate sample sizes. Okay, and this is not a simple nonlinear problem. Like papers on running this algorithmically were in Nature a few years ago. So it's recent stuff, and it's very robust. And here we didn't do gradient, we did PCN, another MCMC scheme that I won't talk about too much. Okay, so, but that's sort of the algorithmic package. And of course, what I've said before already, what they really want is they want error bars for the outputs. Yeah? So they need uncertainty quantification because they have these multi-step measurements and they need to know at each step how well they've done in their recovery. And so, maybe you get a credible set where you just report the curve cloud of all the posterior draws from the MCMC, and you might ask, might now wonder whether these error bars actually mean anything, whether you're on the left-hand side or whether you're on the right-hand side. No? So it could be that you misspecify. On the right-hand side, what we've done, we've misspecified the prior at the boundary, so we expect it to do badly at the boundary, but since these PD solution operators are non-local, the misspecification actually propagates into the interior over here, and so you see that you could get very worrying outcomes when your model is not right. Okay, so the question is really, when people use this in scientific practice, is there any scientific basis for trusting these outputs or not? Okay, and I think this has been around now for at least 10, 15 years. These methods are widely popular, but there's basically almost no theory telling us in these complicated models that we can expect this to work. Okay, and I think it is sort of here where Art's sort of theory on making sort of frequentist guarantees for such algorithms comes into the game, and then I'm sort of following his his work. I have tried to run it sort of on this, run it past these PD problems in the last few years, and it does involve some work if you want to prove things carefully, because this, it's not applied PD. You actually have to start looking into the theory of these equations. But there are three kinds of questions that I think one should be asking if one is wanting to use these algorithms. So the first is just like a sanity check. Is this actually solving the inverse problem? Yeah? So we expect, at least if G is injective, it's not clear yet that when you do this infinite dimensional Gaussian process model that these posterior outputs are actually going to recover the ground truth parameter that generated the experiment. Okay, so does the posterior put its mass at the right point? Or does it sit somewhere else and we're just doing random numbers? Now, of course, the second thing, which is the thing that I've been mostly concerned with in the last few years, is it's nice to prove that the posterior sits in the right place. But in non-convex problems like that, it's not at all clear in high dimensions that these things are computable. Yeah? So you could prove that the posterior sits in the right place, but the MCMC you use is actually never going even anywhere near where the posterior is. So you do need to back up the frequentist guarantees with computational guarantees in high dimensions. Okay, so you want to say, is it actually possible, or is it really true that my MCMC mixes quickly enough that I can say that the empirical quantiles of my MCMC resemble, say, the quantiles of the posterior distribution? Or is it basically, it could well be NP hard, this problem. Yeah? When I'm trying to sample from a high dimensional non-log concave distribution, I can give you, even have some results now, not completely done yet, that is very easy to see without special structure. These are NP-hard problems, so they all have exponential runtime. So the question is, can we leverage PD structure to show that these are, yes, they are nonlinear, non-convex, but you can still do it because there's some local curvature at least, and that's what I will talk about. But a priori, it's not clear that this is even a feasible problem. And the third is, of course, do these error bars mean anything or not? Okay, so are they actual confidence sets that a statistician can accept, or is it just like creating random numbers and being happy about them? Okay, so, and the answer to this question is obviously now after a few years of work on this, and these COVID lockdowns also help to get your teeth into this PD problem, so we made some progress. And typically you really need to understand some of the mathematics of this G map, the solution map of a PD, but also in particular of its linearization. Yeah, because you can already see Fisher information arguments like this pop up. And of course, then you need the usual theory from frequentist Bayes, and we will also need some performance bounds for MCMC schemes in high dimensions when you do actually have log concave targets. So these are sort of the ingredients that pop up. So Ed, how am I doing for time now? Just. Okay, great. So this is sort of the package. I don't know if there are any questions on the conceptual level so far. It's successful empirical methodology, and so I will talk you through a little bit about some of the things we proved in the last few years. And we're really just scratching on the surface, but maybe some understanding emerges. Okay, so the usual way you formalize initially the posterior consistency, which is the first thing you want to ask, is it true that the posterior, conditional on the data, no? So this is a random probability measure, charges a ball around the ground truth that generated your actual samples with a certain radius. We call a contraction rate. And it's not obvious that the contraction rate entails also convergence of the posterior mean. but in particular not in nonlinear problems, but we have tools to prove that for Gaussian process priors in the paper. So typically this contraction rate will carry over also to the same convergence rate of the posterior mean. Yeah? So you can go from the first to the second. Yeah? So that is the first thing you want to prove in these models. Now, so of course the problem is, if I look at Arts and Subhash's book, they will tell me how to recover the G of theta. No? They will tell me how I can solve the regression problem. But I don't want, I want to solve the regression problem too, but I actually want to find the conductivity inside, and I don't want to just know the boundary boundary temperatures or voltages. So I actually need to somehow go back to the theta map, and that is the first challenge here. And so there is sort of a template that we developed in the past few years. In the first proof was for these non-abelian X-rays, but the proof in there is sort of general. And I think if you want to read anything about this, then please go to my lecture notes. And you can grind out at least sort of polynomial type rates in these nonlinear problems for the posterior, where the n, so n is sample size, n to the minus gamma, and this gamma index will depend on all sorts of things like the regularity of the prior, the dimension, and then the ill-postness of your problem, which is kappa, and sort of the inverse stability estimate eta. The key analytical input here is in the box down here. No? So what I've just said before, like in arts theory, the Hellinger distance is sort of the distance in which we naturally can expect the posterior to recover the true parameter, at least if you use a reasonable prior. Now, of course, here even it's not so clear that your prior is reasonable, because you're going to put a Gaussian process on the theta, but then you apply a nonlinear PD map for that, so your actual prior on the regression functions is not at all Gaussian any longer. It's some nonlinear transformation of a Gaussian process. But in the theory, there's some sort of, if you have some regularity of the G forward map, you can deal with this. And then the key input that you need to solve the inverse problem is somehow the compatibility of the Hellinger distance with the distance on the actual parameter. And often in these models, because G is compactifying, it creates uniformly bounded regression functions. And so we are in a nice case where the Hellinger distance is actually equivalent to the L2 distance on the G map. And so what you will then need is some like quantification of the amount of injectivity your G map has, or if you want an inverse continuity inequality, that luckily only has to hold on a bounded set for the regularization norm. Yeah? So for most of these PD maps, when you have such a stability estimate, as we call it, which allows you to reconstruct theta from G of theta, the constant in front here will scale exponentially in age, so it doesn't hold globally. Yeah? So it will collapse globally. So you can't use a global stability estimate. But because you regularize in the right way, you only ever need this inequality on a bounded set, and then there's hope that up to maybe some Hölder exponent eta, it actually tells you that yes, in principle, without giving you an inversion formula, you can reconstruct theta from G of theta. And since the Bayes method doesn't care about the inversion formula, we get this contraction rate from the forward level, and it sort of filters through to the theta level just by virtue of the stability estimate without ever proving an inversion formula. Okay? So it is really just inequalities that are required, and that is sort of the key to all of these proofs. And we've worked this now for at least 6 or 7 representative PD examples. And there's no point in writing a paper for every PD. There's sort of, these conditions are quite robust in a lot of these settings. So this is consistency. So this gives you some hope that this is not completely ill-posed, this approach. Yeah? But it doesn't yet mean that we can actually trust the algorithm. Okay, so and if you want to study computational performance, that's a very hard question, and very little is known. But here's something that we could prove, which sort of comes through the description of local curvature of the posterior near the ground truth expressed through the linearization of the forward map. So of course, again, this G map is just describing a solution of the PD, so it's not clear a priori that I can even find its derivative. No, I mean, so whatever derivative means. But you can use PD theory in its own right to describe some linearization operator, which is again described by PD properties, and let's call this G prime of theta. Yeah, so this is a, you know, if you know a bit of PD, it's not difficult to see that you can linearize these maps. And then we will employ a condition on this linearization, which is gradient stability. Yeah? So I call it gradient stability. What it means basically is not just that the nonlinear map is injective, but also its linearization at the ground truth needs to be somehow quantifiably injective on some finite dimensional space. Okay? And this finite dimensional space is sort of the approximation space you use in your numerical implementation of the MCMC scheme, so it has to be well chosen. And the dimensions shouldn't be too large, n to the a, where I can write down what a is. Depends on the inverse problem. But let's just put this under the carpet for now. So I need an inequality like this. So it will have sort of, if you think of this as, of course, just the conditioning number of the matrix that comes from the G prime adjoint G prime, and it will allow it to go to 0 with dimension. This is something that we need because of the forward smoothing properties of these PD maps means that you will typically have some ill-posedness, and so kappa will depend on the kind of inverse problem you have. So for X-ray, it might be a half. For elliptic problems, typically 2 over dimension or 4 over dimension or something like that. Yeah? So, but you want to say that the linearization of G has some stability in the sense that it cannot vanish except for when H vanishes, and that you can quantify that effect. Yeah? So this is just another identifiability assumption, but through the linearization of your forward map. And we check this condition for several PDs, which is not obvious. I mean, you have to work for this, but it is something that you can do. And when you have this condition, I will give a few more details on the next slide, but you can show that these problems are not NP hard. Yeah? So there are, in particular, concrete MCMC schemes that can compute these non-log concave posterior distributions in polynomial time, where polynomial time means that the number of Monte Carlo steps you need scales polynomially, well, in n. N is sort of the informativeness of your posterior. When n is very large, your posterior is very spiked, and since an MCMC scheme somehow at some point, if you want to compute the mean, has to travel to the other side of the spike, you expect some hardness in the size of the spike. Yeah? So this is something you need to break, and it does break it in n. You also need to scale nice in dimension, because obviously dimension there's typically an exponential curse in dimensionality in all the spectral gap estimates from in ergodic theorems and things like this. So you want to overcome the dimensionality, and of course also the precision level epsilon should come in only polynomially. And for Langevin MCMC, we are able to prove under this gradient stability condition and a few more regularity conditions that these are not NP hard problems. So they are polynomial time computable. So that's in principle good news. In particular, there's a paper by Martin Harre, Andrew Stewart, and Sebastian Former from maybe 8 years ago, where they get bounds like this that are polynomial in dimension, but they actually, if you look at these proofs, they're all exponential in n. Yeah? So in some sense, there's a qualitative improvement over this result. What do we do to prove that? Well, you have to paste things together. Okay. So the first observation is that, like, even if I have a log concave target, so that means that the negative, so for Gaussian prior, of course, this never harms convexity or log concavity. So what you need is the log likelihood, negative log likelihood would have to be convex. If you have this, then it's a unimodal high dimensional distribution. Still not clear that you can sample from it in polynomial time, but there are very important recent results by Anak Dalalian, Alain Demus, Eric Moulin, and there's much work on this since then, that tells you that yes, you can compute these things in polynomial time when you have a log concave target. Okay? So these are very nice results, but our things are not log concave, but we will use it. How do we use it? Well, what does gradient stability give us? If you think we have a least squares problem here, or like a least squares log likelihood, so of course, if you ever computed sort of the Fisher information of this model, you will see that if your gradient stability holds, actually at the true value, where the Fisher information can be characterized either by second derivatives or first, this will give you a strictly positive definite matrix. You get local convexity of the average log likelihood function at the ground truth, and because of smoothness of the parametrization, this convexity extends at least to some sort of neighborhood around the ground truth, simply by continuity, okay? And so then you can use concentration of measure arguments in high dimensions and say, well, actually, that average curvature that the log likelihood has under gradient stability will propagate to the sample level. So here's a theorem in this paper where we did this for the first time. When you have gradient stability and your G map is locally C2, like has some smoothness, which is PD maps all have that, then in that neighborhood, actually, you do have that the whole Hessian of the log likelihood has actually a nice lower bound, of the negative log likelihood has a nice lower bound. Yeah, so it means that these posteriors, at least locally near the ground truth, there is curvature, there is some convexity that comes from the PD. Yeah? Of course, you can write this as a high-level condition, and then you just have to check it for your G map, but we verify this. So in this sense, these problems are not super hard, that they can have multiple sort of modes near the ground truth. No, they actually locally at least look like this, okay? And so this is a theorem, and then you can ask yourself, well, how big is this neighborhood? And you can quantify that as well. But the next observation is, of course, okay, where does the curvature happen? It happens at the ground truth. And where does the posterior put all its mass? Well, it puts it next to the ground truth. So actually, the posterior basically, where it puts all its mass, is locally log concave. So it is local, but it is exactly log concave in the area where it puts all the probability. And what that means is actually, this is already very close in some sense to a Bayesian Mises theorem. No? So you say that locally, basically everything looks like a Gaussian, only that in high dimensions you don't want to approximate by a Gaussian. This is too restrictive. I will explain why if I have the time at the end. You want to just approximate by something log concave, which for these gradient methods is just as good. So what we have a theorem here that says that if you think I take this curved thing and then I just concavify it around, and I sort of neglect the fact that somewhere it will not be log concave any longer. Well, if I do that, I make an error, but since the posterior puts all its mass where it is log concave, this error is not very large. So I can just forget about the non-log concave part of this posterior distribution. And the Wasserstein distance, which is the crucial distance to study gradient dynamics in spaces of probability measures, is very small if I can sort of construct this log concave approximation. Yeah? So it is not just like polynomially small like in a Bayesian Mises theorem, but it's actually exponentially small. Okay, so I can, Bayesian Mises theorems tell you approximate a posterior by a Gaussian, but the class of Gaussian distributions is finite dimensional. The class of log concave measures is infinite dimensional, and that makes a difference here. So you can get much faster rates, and this approximation is really very good. It's exponentially going to zero in sample size. Okay, so now, of course, in order to construct this I can construct the proxy measure, but if I want to use it for sampling, I need to like numerically construct it, and this is where you need to initialize. Yeah? So you need to find an initializer for your problem, which doesn't have to be as good as the posterior itself. It just has to lie in the region where your curvature holds, which you can check for your PD. And for Schrödinger equations or some examples, we check that these initializers can be constructed by much simpler means than studying posterior contraction. And now what you do is you just run your Langevin method on this proxy posterior, which for most of the posterior surface is exactly the same as standard Langevin. And we can quantify this by a concentration inequality. So you take a H function that is Lipschitz. Say if it has k entries, then it's Lipschitz in each coordinate. And you will get a nice explicit exponential bound with all constant scaling polynomially. I don't want to go through the details, it's a bit technical, but you basically can show that there's a sort of sub-Gaussian estimate for these ergodic averages coming from gradient MCMC. And so in particular, if you take for your H function the identity function, which is Lipschitz in each coordinate, you get a computation time guarantee for the ergodic averages after some burn-in, which also scales polynomially towards the posterior mean. Yeah, so what it means is that well-initialized gradient MCMC will break the curse of dimensionality in these problems. And you can prove it, and you can check the conditions for PDs. You can ask yourself, of course, what happens to cold start initial? So if I initialize in the wrong place. Well, I mean, there's a theorem. I was discussing this with Afonso Bandera at ETH Zurich this spring, and also Gérard Benarous has some recent papers on this, so where they show in statistical physics models, which are very unrelated to what we do here, but not still there's conceptually something similar, that you can actually often show that worst case MCMC will always be exponentially slow unless you're really explicitly log concave. Yeah? And this is not, so if the step size of your Markov chain is less than a certain sort of thing that you can quantify, then it will always take an exponential time if you start too far away to travel to the center of the posterior where it has its mass. Yeah? And you can show this by an explicit lower bound on hitting times, so that these are actually NP-hard problems. So you cannot expect cold start MCMC to work here, which means the question of initialization of MCMC schemes in such non-log concave settings is one that one has to address, at least in the theory. Yeah? So it's not something, you cannot like give a unified theory. So like cold start and warm start MCMC performance are two different cups of tea, but for like well-started MCMC in these PD models, we can give explicit computational guarantees. And these are not NP-hard problems. And I'm not saying one should use this gradient method explicitly, but if you want to travel over a huge spike, you can expect that at some point you will need a gradient that accelerates you when you want to get on the other side. Yeah? So I would be interested if anyone has suggestions for MCMC methods that are not relying on gradients at some point. Okay, I don't have really time for the last part. Is 2 minutes or how much? 5 minutes. I just want to, so this question of credible sets, confidence sets, I've talked about this many times. There's this Bayesian Mises theorem. I just want to conclude with one thing, which is sort of a slight surprise to me. if you think of what I've done, I've basically said that, okay, the posterior is very complicated, but somehow we expect it to look a bit bell-shaped, at least locally, and I can quantify this in high dimensions explicitly to get computational guarantees. Yeah? So when you prove computational guarantees, you want to exploit statistical properties of the posterior distribution. You don't want to treat them as a worst-case distribution. You want to say, well, actually, this is a posterior distribution. It has nice statistical properties from the theories. Let's use it when we give computational guarantees. Let's not put this under the carpet just because we don't want to read Art's book. Yeah? So you can, of course, then say, okay, well, this guy is just doing bench transformesis. But this is actually not true. Yeah? So the theorems we have, as you're going to receive from the faster convergence rates that we obtain, they're not bench transformesis theorems. They're really different. And in fact, for one of these PD examples, when you do bench transformesis in infinite dimensions, it's kind of tricky anyway. But typically, what you need to do, you have to sort of show that the information operator has sort of some surjectivity properties. You can find the inverse Fisher information if you want. And you can ask this question already just in simple directions in your space, not the whole matrix or operator, just like take some test functions that are nice. And typically, you need to check a condition like this. And we have some nice sort of so-called semi-parametric bench transformesis theorems for some of these PDs. You can go to this other paper with Mona and Patanine. But this is often very hard to show that this Fisher information operator has an inverse, but we did succeed in some examples. But then we found that in these very most standard elliptic PD examples that everyone uses in applied mathematics, you can, of course, ask yourself, is the Fisher information operator, does it have an inverse? Huh? So you just look at this elliptic PD from the beginning. You want to find theta from seeing the solution of it. You can prove everything is a nicely injective problem. So Bayesian inversion is consistent. You get contraction rates. You can even give computational guarantees along the lines from these log-concave approximations. But bench transformesis theorems are false. Why? Because the Fisher information is not invertible, even in the most trivial directions. Yeah? So there's a nice condition in a paper by Art from, I think it's technically his PhD thesis, that there's this adjoint score condition that you need to check for you to whether you can get a root n consistent estimator of a functional, and that is also a necessary condition for a bench transformesis theorem to hold true even just for a simple functional. And what we show is for this basic PD, when you compute the score, the linearization of the forward map, and you take the adjoint, you get some nasty PD structure that actually, even for like super nice, so the ground truth theta is just constant, so the easiest function, the Laplacian. The test functions can be any positive smooth function that vanishes just along one ray. Yeah? So if you have compact support somewhere, this is already done. Yeah? So, and for none of these functions will you get a bench transformesis theorem. In particular, the cylindrical distributions in infinite dimensions will not approach a normal. And also, this is not just a problem of the Bayes method. Root n consistent estimators do not exist. Yeah? So then you might think for a while, well, this PD is too hard or something, even though it's the standard textbook example that people use. For this operator, the inverse Fisher information doesn't exist, but it has to do with the infinite dimensional nature of the problem, because this gradient stability condition and the log-concave approximation still is valid. Yeah? And this is written up in the lecture notes, so you can look at it there, both the counterexample and the log-concave approximation. So what that means somehow is that in high dimensions, one has to be a bit careful using this Lecam theory of Gaussian approximation of experiments. This doesn't always work. Yeah? But it doesn't mean that you still have curvature. You could be locally bell-shaped or maybe even Gaussian, but somehow not in a way that converges to a well-defined limiting experiment. So I think, in a nutshell, this is leads to me to advocate non-asymptotic techniques in the study of these posterior distributions rather than asymptotic ones. Okay, well, I can only say that we understand very little, but we understand a bit more than maybe 5 years ago. It's also not cheap to write papers in this area because you do need to learn some PDs. Here are some of the papers. But I certainly think that it's a very interesting topic for both theory and also for applications, because of course the higher the more complex these data sets get, the more reliant are you on good MCMC schemes. And I would be very curious if one can somehow design some other, like get such computational guarantees for other things like Hamiltonian Monte Carlo or so, or whether the gradient structure is really crucial to deal with this sort of informative limit as n goes to infinity. So I think also for MCMC performance, there are lots of open questions because we only have one result so far. And I think I'll end here. So thank you.
Thanks for the talk. I was curious, your result that says that you cannot get, you've got this curse of dimensionality for the result with Banderas. Yeah.
I mean, I'm writing this proof at the moment, so I didn't write a careful statement, but yeah.
Okay, but so you say it's true for unimodality?
So you can find unimodal posterior distributions where statistical, like actual posterior distributions that are unimodal around the ground truth, yeah? Or not the ground truth, around the posterior mode, yeah? But not log concave, yeah? So of course this could be, yeah? And if you start the MCMC too far out, even the hitting time of just getting through the foothills before you get to the spike scales exponentially already by an argument that comes from statistical physics, and this requires that the dimension over n is constant, so d shouldn't be little o of n. But when the dimension is genuinely large, there are these free energy barriers, as the statistical physics people call it, and Gérard Benarous, this paper is from the Annals of Probability, where they show this in a tensor PCA model, but this principle actually works also for Gaussian process priors, and such posterior distributions. You really need quantitative log concavity to rule out this computational barrier. And it's not a question of multimodality that creates computational hardness. It is just a question of you not going quickly, like ascending quickly enough towards the mode. And this is something that works not just for gradient. This works. We can prove no MCMC scheme can beat that barrier. And the paper will be done in the summer.
Okay, so even if you do tempering and things like that.
No MCMC of sufficiently small step size can ever travel to the bulk of the distribution.
Chris.
Thank you. So you mentioned a few times about uniqueness of solutions and injectivity, and so a couple of just two related questions. First of all, does the prior not kind of this Tikhonov regularization, does that restore well-posedness? But moreover, in statistical problems, in particular Bayesian, if we see that there are classes of solutions which have the same posterior, so there's a whole class of solutions, that tells you something about the experiment, either that the experiment that you've done is not able to distinguish between classes of solutions, which says actually maybe there's another experiment I need to do in order to then distinguish between these solutions.
Yeah, these are excellent questions. So, or maybe remarks. I mean, so the first is, so as I've said, the stability estimate. So let's suppose even you are injective, the stability estimate will always collapse when you take the infimum over the whole parameter space. And the Tikhonov regularizer or any kind of regularization method will insist that any solution you ever consider for theta stays in a fixed bounded set. And so on that bounded set, you will have well-posedness. So this is why I say regularization is important, because if you don't regularize, if you just do unpenalized least squares, you will run into the fact that the injectivity collapses as you optimize over the whole space. So you need regularization. Actually, you need to even amplify regularization in hard nonlinear inverse problems beyond the standard Gaussian prior. So that's perfectly correct. And this is the same for Tikhonov regularizers as for posterior distributions, because the prior has the same effect. The second question, I mean, So I completely agree that when you have an unidentified model, the MCMC ought to, or hopefully will show you that when you run your MCMC by like sort of maybe clustering around several of the potential modes. But it could also be that you miss some. And so, I mean, if you say empirically this is something that you see in practice, well, that's good news. It means that you expect some robustness of the MCMC towards such lack of identifiability. But I mean, how can you know that you're not missing out on lots of other modes that the MCMC never shows you? So I mean, I think one needs, and in fact, a lot of these inverse problems have inbuilt what they call gauge groups. So there's a genuine identifiability issue in your parameter space. You cannot choose a prior that is gauge invariant because it's a nonlinear constraint. So this is not something you can do. So you do want to have some methodology that is provably robust to identifiability issues. And I mean, if I agree with you that MCMC is certainly a candidate to be robust to it, but I think it will be important to give some guarantees for its ability to pick up such issues. But I'm not saying that you're running blindfolded when you do MCMC, but I don't see a reason why I should trust it without making some analysis at least.
Any other questions?
Thanks. Yeah, I'm very pleased to see this development. we're playing around with this a bit in the 90s, but now it has really taken off, and I'm very pleased to see all these results. So thank you very much for your lecture and the overview. Now, the next question is on computation. Is there a hope that combining all this with, say, particle filters and sequential Monte Carlo methods, that we could get some proper weather forecasts?
I mean, sure. I mean, I won't forecast them now for you, but I mean, I think, of course, the data assimilation is. Where was this? No, I mean, so that was one of my examples, and in principle, you can write down the differential equations that these are either, when you acknowledge the probabilistic structure, these are SPDEs, so stochastic partial differential equations, or you can also try to write it deterministic dynamics and do like Navier-Stokes is maybe the best model example. I'm actually just now this summer working on Navier-Stokes with one of my colleagues in Cambridge who luckily is an expert on that. So I think you can't check, for instance, this gradient stability condition for Navier-Stokes and weather forecasting PDEs, like, they always write like 50 equations and it's like a very messy system. So, so I'm not going to like deal with the most complex case, but the PDE structure that I have here that tells you there's some local curvature should also hold in these data assimilation applications in principle. Whether that means you can use a particle filter requires more sophisticated probabilistic analysis, because the results I have so far is for these gradient-based methods, which are kind of different.
Yeah, well, I think, I mean, the point is with standard PDE methods is that they work under certain boundary conditions, but these boundary conditions has to be very special types of boundary conditions. Whereas the real boundary conditions that we need, effectively, we get meteorological measurements all the time, and they come in streaming. So if you have a streaming MCMC to follow that, you should be able to, I mean, yeah, I can, sure. It's the usual thing, they say that there might be possibility of snow, and you look out the window and there's a blizzard, right? And that, I guess, should be avoided.
I mean, avoidable. I have no reason why I should not think that one cannot also do this at some point, but it is, of course, a very hard problem, so I can't give a quick answer.
Sure, absolutely.
Okay, so if I understood correctly, I mean, I'm not an expert at all in this field, so the assumption is that you are able to solve perfectly well the PDE, while if what I know from colleagues of mine is that they typically are not able to solve it. I mean, at a fine grid, let me say so. So, can you consider this item too?
I mean, okay, so that's also a very good question. I mean, so I said this somewhere here, in the second bullet point. I said we can evaluate G theta by numerical PD techniques. So by this I mean that when you run your MCMC step, you will need to evaluate the log likelihood function, and at that point you need to evaluate G of theta. And of course, in my theory, I take this as one algorithmic step without errors, because I'm only trying to study the Monte Carlo error. So I'm not looking at the actual numerical PDE error. Now, of course, you will want to solve this within a certain precision, and this will also propagate into the ultimate inference. But solving these PDEs this is basically a matrix inverse you're computing, so it's not like a NP hard step. So for me, the first step was to show that these are polynomial time problems, that they're not like unfeasible. And the numerical forward step is usually cheap. Of course, if you want to do an overall diagnostic of the whole algorithm, you will need to factor in the discretization error here as well. But this is a very well-studied problem in numerical PDEs, and we have bounds on this that I can just feed into my results. So this is not really the issue in this context. I just take this as one algorithmic step that the numerical PDE person is able to do. But this is a very good question.
Anybody else? Okay, well, let's thank the speaker for a fantastic talk. Absolutely. Congratulations.